as Ronald already said, I'm coming from the University of Alcalá. It's a really old university close to Madrid. It was founded in the 13th century, and since then we haven't had traffic studied yet. So, okay, this is the team. So first of all, present the team, and Pablo is one of my colleagues. One of the students have helped me with the study, and we are a computer science and electronic engineer team, because we don't have these transport studies, but we are focused on simulation and AI-based research applied to different markets. So we have done this for transport and for other things like telecom networks and so on. Okay, so after this introduction, why it's important, the low emission zones, it's clear. So for me, it was really nice, this drawing from the European Environment Agency that is telling we are about to die, because this is our life expectation reduction. So low emission zones are really important because they are conditioning our lifetime. So after this, we were thinking, what is the balance between emissions and travel time? So in many ways, authorities are designing low emission zones based on political reasons or historical preservation of the urban environment, but the price is paid by the user. So we have we need a balance between these low emission zones and travel time. So this is the research question. So how to reduce these areas at the minimum user cost. So, and this is for sure what is happening, at least in Spain. So you have always owned the emission zones. So sometimes you find the streets that are cleared, but the emission zone is still active. So the question is, why couldn't we have dynamic low emission zones that are afterwards delivered in some way to the traffic drivers? So the problem we face in these stages, really classical. The first one is to collect sensor data, make the traffic flow calibration, then calculate the optimal LEZs, and then generate and distribute route signaling, or maybe we can discuss a bit later about this. So having colored traffic maps, that is not the scope of this talk, but it was my PhD, so if someone is interested in this, having traffic colored maps or differential traffic routing, we can talk a bit afterwards. So our talk today is about this optimal LEZ calculation. Why? Because we hadn't done enough for make the calibration. So yeah, for us it was really well, we can separate both things. So we are going to talk about this, and we are going to use non-calibrated flows, synthetic data, because we are interested in the procedure of how to calculate this dynamic and optimal LEZs. So the process is also rather classical, because we have the network, we have the demand, we have the emission standards. We are using the standard SUMO emissions, the vehicle types, and the regulatory constraints and urban policy. And this was for us a really hard constraint, because we are facing that when you design these dynamic low emission zones, those constraints are limiting the algorithms that we were to use. So the objective is to have the emissions under the acceptable threshold. So as well, we should cover the most polluting edges or roads, so having the minimum impact for travel times. And these were also really hard to cover, because the LEZ edges, so the low emission zone must be a continuum area, a single continuum area. So yeah, you need to focus on the topology as well, and other constraints that are fulfilled, and that we will see them later. So the main loop is this way. The problem is taking the traffic network. We use the standard LEZ, that we call the SLEZ, that is the political LEZ that is pre-established, and these model constraints that we will see a bit later. So we enter a genetic evolutionary algorithm to create LEZ proposals that are evaluated with SUMO. So we use SUMO as a validation tool, simulation and validation tool. So whenever SUMO ends the simulation for our purpose, then we collect data, extract the KPIs, and follow the whole loop just to find the optimal solution for our LEZ. And it's expressed as a TAF definition, a traffic area zone. We tried in the very first beginning with a linear programming model, but it was really hard to implement this. I don't remember who also introduced, I think it was Christopher, who introduced the linear constraint model. But explaining the topological constraints in the linear programming model was really complicated and made no sense. And when the city size was increasing, it was really incredible how complex it were. And also we prefer to use this evolutionary approach. So the mix, it was interesting for me, the mix that you told before between linear constraints and the evolutionary algorithm, because it's nice. Okay, for the evolutionary algorithm, the most important thing usually is how you design the chromosome that is going to be evolved inside the system. And what we represent in the chromosome is one position for each edge, and representing the status in a binary way, so inside or outside the low emission zone. So we consider the whole set of the edges, then we detract the number of edges in the excluded region. So it makes no sense to have the calculation for the whole city, but only for the perimeter, for the polygon that you're going to consider inside. Then you will always be including the highest emission zone, so it's not necessary to make the reasoning about the edges of the road that you know in advance that will be included. And also these other edges or roads that must be legally included. For instance, the historical data center, pedestrian ways, and all this stuff. So you have a restricted model, and then you apply over the model, and in the simulation you need to apply the fitness function, and to combine the emissions ratio and the waiting times, well, the travel times, we selected not the real travel time but the waiting times, because they are really related to emissions and the waiting time. So we use a very simple linear model with weighted model, and with that was the fitness function that we were about to optimize. And also all this stuff was made using the Python implementation with NumPy for the genetic algorithm. So let's go. This was the foundational scenario, the model. Now we are entering the simulation. For the simulation, we are in the middle of Madrid and another head of province, that is Guadalajara, not the Mexican Guadalajara, but the Spanish Guadalajara. That is really interesting scenario because it's a head of province, mid-size, so 90K population, and it's crossed by the main Spanish highway connecting Madrid and Barcelona, and it was really interesting because it's becoming a logistic center, really important logistic center inside the country, so it was perfect for our simulation. So we created these stats according to the activity model. So we created the necessary stats, and in green you can see the standard LEZ. So this is the standard LEZ that the authorities created this year inside the city. So yeah, you can find here the edges just to know about the size. What's on in the standard LEZ, so the political low emission zone? It has a really big coverage with full of cameras, 80 detection smart cameras, We are still not getting this data, but in the next future we'll do. So we haven't calibrated yet the traffic flow, so we are just using synthetic flow, as you will see right now. But yeah, this is the statement of the problem. And we have our reduction objective that was set in the political side was the 40%. For us, is one of the constraints that is going to be met. So the traffic also has several exceptions, that is, the resident population can enter, and also restricted guests, workers and business, taxis and service vehicles. So this is the standard length. But the constraint that we need to add to the model is, yeah, topological connectivity. So we cannot create LEZ in unconnected aisles. So if you don't add this constraint and you put the optimizer into action, then it will create several unconnected aisles. This is not a low emission zone. These are low emission aisles. So this is a hard constraint. So the historical area as well. There is also topological bounding, as geofencing for where the LEDs should be inside. The volume bounding for the coverage of the whole area, and this is also a political constraint. And the emissions bounding, that it was the target. So the synthetic demand, so we just planned to compare scenarios. We created a set. Well, this is not that important as this. So we created a t-shirt sizing for the demand. So just to create several different scales for demand. So all the experiments that we're going to see we'll use the medium size. But then we will see what the effect on the other sizes of the demand. And this is the vehicles distribution for the model. We use the HBFA emission model that is inside SUMO, so we didn't use anything complicated. We just designed the electric vehicle with the Kia Soul model, and we took this traffic demand, the 20% that is more or less realistic, and the rest is just a synthetic distribution. So, in the same way, we have already seen part of the evolutionary algorithm, so I'm not going to stop here very much. So, but just to have the full genetic engine is just create your evaluation, see if it is valid or not, and then enter the genetic for the selection, mutation, crossover, applying the constraint, see the feasibility. The algorithm is not always providing feasible solutions, so whenever the solution is not fitting, we enter again in the loop. And then the new LEZ proposal is simulated by SUMO, extracted the measure, and then if it works properly, we would have this optimal LEZ configuration. We are entering the results. Well, in fact, we have here also the parametrics for the evolutionary algorithm. Yeah, if anyone is interested in this, I think that the most important thing is that here we have the topological boundary. It's more or less this. This is the fixed edges, the historical part that need to be considered. And in this other green, light green, or yellow green, is the result of the simulation. The most interesting thing is that this optimization with the evolutionary algorithm is converging quickly. We use a really high number of population, that is initial combinations of edges that could be part of the low emission zones, and the evolutionary algorithm iterates over them and also create new ones during the execution, and it converts really quickly with a standard deviation that is really controlled. So it makes sense. And if we compare both low emission zone, then here's our surprise. So this is the standard one. This is the optimized low emission zone. So for the M demand, yeah, we are getting a really smallest zone. So yeah, this is what we will take to the authorities to say, yeah, why we don't change this fixed schema into a more practical one that will preserve the service for our population. So, getting to the measures that we were considering, we need to consider in both ways the emissions improvement and also travel time improvement. So here you have pair statistics and expressed in an histogram. So here 0 means that, well, I need to stop a little bit. Both scenarios, the standard LEZ and the optimized LEZ, are compared to an initial scenario where no LEZ is designed, so to have a baseline. So no emission zones against the standard and the no emission zone against the optimal, just to have the same comparison base. So we can see in the red side that the red means the standard LEZ comparison, how we have enhanced relatively the emissions, and in green, how the optimized LEZ is reducing emissions in the network. So we can see clearly that even having a smallest region for protected region, we have less emissions because it's optimized in fact. So we have also this part, these emissions are increased for the vehicles in this side because of the setting of the low emission zone. Because if you are protecting part of the network, some part of the traffic will need different routes that are circumventing the low emission zone. So yeah, these vehicles will have also bigger emissions. But yeah, it's the final result is that we are experiencing a really big improvement. We face into the travel time. Travel time is rather leptocortic because we are considering the whole network for the simulation, and many of the vehicles are not affected by low emission zones. And we have a slight benefit with the optimal low emission zones, as you can see here that the green is clearly better than the red one, and also that those vehicles affected by the low emission zone settlement, they will be impacted anyway. These are not so clear, but if we combine them in this graphic, this is the medium size demand, yeah, then it's clearer. So if we have here the relative travel time impact, so this is how they are impacted in the mean. We are showing mean values. And also here are emissions. We consider CO2, but you can use any of the pollutants or the emissions that are present in the model. It's not, you can use any one of them. But what we can see is that the model using the optimize not only is about having a less geofencing for the low emission zone, but also is behaving much properly. So we have better emission reduction and we have better travel time impact. So both are impacting, but with the optimized model, then you're getting better results. So yeah, you've got here numbers, but numbers are just numbers. I prefer the graphic. And how it looks like, yeah, it's not that clear. If we zoom out, then it is much clearer. You can hear in green. So if you don't see it, it doesn't exist. No? As Dr. Jones said, it was like this. Okay, so this is the grid path for the standard low emission zone. Here is the optimized, and you can see how different are the traffic profiles. So adding the constraint in the optimization algorithm is bringing new possibilities for this experiment. Where are we now? So we have seen so far this optimal LEZ calculation algorithm. Now we are working here in the traffic flows calculation. We are not pure transport engineers. We are computer science and electrical engineering. We are working in AI-based traffic flow calibration. So We have several models, well, 7 models in fact, already tested here. It's not for today's presentation, but just to open Hungary for the AI-based learning. The latest figure that I've got is our models are achieving yet 65% success calibration rate for using SUMO as an engine. So we use SUMO to generate data sets for training the AIs. And yeah, it's good, but not enough. And so we will do this. The mesoscopic behavior of SUMO is a challenge for us. We need to work further there, because for creating the AI-based data models requires mesoscopic simulation. We can do this in the microscopic way. And also, we are working there. We are revisiting. We are not facing the road signaling, but revisiting my PhD, in fact, that is about how to create colored maps, traffic maps, using this optimal LEZ calculation. So this, and future works. So it's just creating dynamic access, so a dynamic behavior. So how the dynamic LEZ is evolving during time, using different demands. We are also working actively on creating the LEZ constraint using graph databases. This is a really nice thing, because we have access to really good data for geographical data expressed in graph databases, like Neo4j and these kind of databases. And yeah, having bigger scenarios and to adapt these LEDs to environmental conditions, and yeah, to calibration that I already told about this, and maybe in the close future, if we find the good collaboration, having nice traffic signaling for this. And this was all. If you're interested in what we are doing, you can find us here. We are small, but very powerful, and open to any question that you can have. We have a lot of papers published in not only for traffic, but also for pedestrian management, in crowd evacuations, in emergency, but maybe if someone is interested in this, we can also help.